solve the problem in quiz number 4. In that case, we had 2 springs and 2 masses. And like one of the masses is like a pendulum that is connected to the other mass. And what is asked is equations of motions using Euler-Lagrange equations. So to handle these problems, remember the first thing that I need to do, I need to write down the position vectors for these objects, for this capital M and this small m. And to do this, usually using a coordinate system facilitates our solution. So first let me put a coordinate system. Now remember, the x shown here is the displacement from the equilibrium position for both of these springs. So when x equals 0, the left spring and the right spring, both of them are unstretched for this particular problem. So then a good selection could be like putting the origin at this point. So let's say here is my y, and here is my x. Okay, so in this coordinate system then, and as long as you have a fixed origin, the choice of axes, like their directions or the choice of origin shouldn't matter. But usually there is like a simpler coordinate system, and this is like the simple case. So then I should write for the first object. So I see that it is located at on the horizontal it is located at xi, and on the vertical it is like 0 times j, right? So it is simply xi. And for the second object then, I will have, so for second object I can express this as this first vector a, and from here to here as the second vector b. And for, of course, b, I have here d sine theta, and here I have d cosine theta. Okay, so now I can express R2. So R2 is, so I have x plus d sine theta in the I direction, so x plus d sine theta in the I direction, and on the negative y direction I have d cos theta, so minus d cosine theta j. Okay, so why do we need these vectors, position vectors? Because we want to calculate the velocities so that we can calculate the kinetic energy, which is then used for the Lagrange function. Okay, so the v1 is easy, so it is going to be simply x dot in the I direction. So v1 square is simply x dot square. Whereas the velocity for the second object is dr2 by dt. So I will have x dot plus d cosine theta theta dot on the I direction, and plus, now I'm basically taking the derivative with respect to time and using the chain rule here. So cos theta makes sine theta, d sine theta theta dot. Notice the sign change because derivative of cos theta is minus sine theta, sine theta. Okay, then so the vt square is of course vt inner product with vt, so it's going to be x dot square plus 2 x dot d cosine theta theta dot square plus d square theta dot square. So I will have cosine square and sine square theta here. So they are just going to be 1. Because like 1 from d square cosine square theta theta dot square and d square sine square theta dot square. And I know cosine square plus sine square is 1. So I can write it like this. Okay, so then I can basically express my kinetic energy then. So the kinetic energy is going to be, so 1 over 2 the mass of first object, capital M, and its velocity, so x dot square, plus 1 over 2m, now like this entire thing, so it's going to be x dot square plus 2 x dot d cosine theta, theta dot square, plus d square, theta dot square. Now I also need to write the potential energy. Now in this case there are two different mechanisms for potential energy. One of them is the elastic potential energy stored on the springs, and the other one is the gravitational potential energy for this little object, little m. So first of all, so like for elastic, it is of course 1 over 2 k x square for the first spring, because it's, for instance, elongating. But the other one is going to be compressed the same amount, so it's going to be 1 over 2 kx square as well. So the elastic potential energy is simply kx square. So I will have kx square here. But that's not all. I also have the potential, gravitational potential energy, and I can write it directly because I know the y component of the position vector for the second object. So it's just like d minus d cosine theta. So all I need to do is just multiply by little m minus m dg, maybe let me write minus mg d cosine theta. Okay, great. So now I have the kinetic energy, I have the potential energy. I can basically calculate the Lagrangian and obtain the equation of motion. So let's see how we can do that. Okay, so too much. Okay, great. Maybe that. Just a little bit. Okay, well, I guess this is it. Okay, so now remember, Lagrangian is t minus v. So this is going to be, so it's going to have like 1 over 2 big M little m x dot square plus m d cosine theta x dot theta dot plus md square over 2 theta dot square minus kx square plus mgd cosine theta. Great, so this is my Lagrangian. Now question, how many degrees of freedom do we have? Answer 2, we have both x and theta, so we should have two equations. So the first equation should be, for instance, d by dt partial L partial x dot minus partial L partial x equals, now we don't have any non-conservative forces other than constraint forces, but constraint forces do not contribute to the generalized force, so it's going to be like qx, but qx is 0 in this case. And similarly, so we also have d by dt partial L partial theta dot minus partial L partial theta is q theta, but again in this case q theta is 0 because we don't have any non-conservative force in this problem. So I will need to just evaluate these partial derivatives and equate them to 0. So it's just like, it's kind of long. I mean, not too long, but it's like straightforward. That's the important thing. Okay. Okay, so let's start with the x equation. So to get the x equation, maybe, okay, so to get the x equation, so let's first see what is partial by partial x. So I will have m plus m x dot plus m the cosine theta dot, right? So I'm just like looking at where I have x dot explicitly. I have only the first two terms, x dot here, x dot here. Okay, so now I should evaluate then d by dt partial L partial x dot is, it's going to be the full time derivative of this expression here. So masses do not change over time, so they are like this, x double dot plus. Now be careful, although for the first partial derivative I take the partial derivative for x dot. Now I'm taking a full time derivative here, so d by dt. So like whatever depends on time, I should take the derivative of that quantity. Now in this case, both the cos theta and theta dot depends on time, and the derivative of cos theta is of course, you know, sine theta dot. So it's going to be minus md sine theta. Now theta dot, but another theta dot I have got here, so theta dot squared. So this is for the cos theta, but I should also take the time derivative of the second term. So plus md cos theta double dot. Okay, great. So this is one. So okay, so the next thing I should evaluate is of course partial L partial x. So this doesn't depend on x, doesn't depend on x, doesn't depend on x. Only this one depends on x, and this is minus kx. Now I can combine these equations, and then I can write down m plus m x double dot minus md sine theta dot squared plus md cosine theta double dot. Now minus partial L partial x is plus kx equals 0. So this is my first equation of motion for x dot. But of course it's like coupled to the theta dot as well. Now I should also do the same thing for theta. Okay, so let me just try to write it down here while I can still see the Lagrangian. So partial Lagrangian partial theta dot is, so I have md cosine theta x dot plus md square theta. Okay, good. And partial L partial theta is, so I have like theta here and here. So it's going to be minus md sine theta x dot theta dot minus mgd sine theta. Okay, so now I can go down a little bit. Okay, so now I should calculate d by dt partial L partial theta is like, now it's going to be md cos theta x dot, sorry, x double dot. But I have forgotten, like I should also take the, okay, let me see, x double dot minus md now for the cos theta term sine theta dot x dot plus md square theta double dot. So this is the first term, and minus this term, of course. So like then I will have d by dt partial L partial theta dot minus partial L partial theta equals, so like I should subtract here, But look at this while I'm subtracting these. So this first term will cancel out with this term, so it's going to be a simpler equation. So it's going to be md cosine theta x double dot plus md square theta double dot plus mgd sine theta equals to 0. So this is my second equation of motion, and which is evaluated for theta dot. Okay, so then I have two equations. So these are coupled equations, but they characterize the system fully. And like if I had the initial conditions, then I can numerically integrate these solutions and get the trajectory of the system. Okay, now on part B of the problem, we have two non-conservative forces applied to the system, Fa and Fb, and the question is to calculate the equation of motion. So now it's going to be similar to what we have done beforehand. So let me just show you. Remember, we have the Lagrangian here and Lagrangian Euler-Lagrange equation here. Now in this case, Qx and Q theta, and of course these are like non-conservative, are not going to be 0 anymore. So for instance, I will have d by dt partial L partial x dot minus partial L partial x should be Qx non-conservative. And like the left hand side is exactly the same as before. So you know what we have obtained here, the left hand side is going to be the same, but the right hand side is going to change. So the right hand side is going to be the non-conservative generalized force for the generalized coordinate x. And similarly, full-time derivative of partial L partial theta dot minus partial L partial theta Q theta non-conservative. Now again, in this case, the left hand side is the left hand side of this equation in boxed in green, and the right hand side is going to be a generalized force for the theta with non-conservative forces. Now remember for the kth generalized coordinate, the generalized force is over all forces. So I will need to calculate the partial Ri by partial Qk, and I have inner product. Now I is over all non-conservative, non-constrained generalized forces. So in this case, these are Fa and Fb. So what are Ri here? Now remember, this formula was derived from virtual work. So Fi, inner product with this dRi should be on the order of like work. So this, this Ri here is actually where this particular force is located, where it is applied to, where it is being applied to. So for instance, for Fa, now let's say this is my origin. So now I'm going to draw the Ra for Fa. So it's going to be, so I will start from here and it will come to here. So this is my array, and Fb is applied to this point here. So Fb is going to be, so Rb is going to be this vector, okay? So then here is the name of the game. So Qx non-conservative will be Fa inner product with partial array partial x plus Fb inner product with partial Rb partial x, and also I will have for Q theta non-conservative FA inner product with partial RA again, so RA doesn't change, but theta changes, partial theta, plus FB partial RB partial theta. Okay, so not too bad. So all I need to do is I need to calculate these partial derivatives of RA and take those inner products, and then I will be done. Okay, so let's go down a little bit. Okay, so let's write RA and RB. So we have actually calculated them before because they happen to be the positions for these particles, but they don't have to be in general. So let me just calculate them. It's easy. So it's going to be x plus d sine theta in the I direction and minus d cosine theta in the j direction. And I also have RB. RB is simply x in the I direction. Okay, so let me just calculate the partial derivatives. So partial RA partial x is simply I, and partial RA partial theta is d cos theta in the I direction. So minus makes it plus, so plus d sine theta in the j direction. Okay, so these are for RA. Now for RB, so partial RB partial x is 1 and partial 1 in the I direction, so it's just I, and partial RB partial theta is of course 0. Okay, so what is FA? FA is the FA in minus x direction, so it's going to be minus FA in the I direction, and FB here is FB in the I direction. Okay, so now I have everything I need. So then I can write Q non-conservative x is going to be, so Fi inner product with Rix, so first of all this, so it's going to be minus Fa, and FB inner product with partial RB partial x, so like these two guys, so it's going to be FB. Okay, perfect. Then from here I can write d by dt partial x dot minus partial x. Now this part we have calculated in part A above, like before, is going to be, qx non-conservative, and in this case it is simply fb minus fa. And it makes sense because both fb and fa, so like fb is trying to increase the x and fa is trying to decrease the x as well. So like fb minus fa. Okay, so let's also do this for q theta non-conservative. So in this case I will have again here, fa inner product with partial RA partial theta. So here is my partial RA partial theta and fa. So I will need to calculate the inner product. I inner product with I is 1, I inner product with j is 0. So I'm going to have minus fa d cosine theta here. And the second term, fb inner product with partial rb partial theta, but partial rb partial theta is 0. So I don't have any other term, so I have like just 0 here. And from here then I can write partial d by dt partial L partial theta minus partial L partial theta is q theta non-conservative, and it's going to be minus FAD cosine theta. And if you think about this, it's going to be basically like d cosine theta is this distance. So it's going to be the moment of FA with respect to like this hanging point. And it has a negative sign because FA is trying to decrease this angle theta. So it makes sense. And again, the left hand side, so we have calculated them before. So like, you know, the left hand side of this expression comes for the x, and the left hand side for this expression comes for the theta. So you see, it is, I mean, it's not too difficult. It's like a little bit, you know, you need to do a little algebra here, but it is more or less straightforward.